This is the video for Part 1 of Section 8.1, Congruence and Lagrange's Theorem. Recall that for a positive integer n, two integers a and b are congruent modulo n, which is denoted with the notation shown, provided that n divides the difference a minus b. Now, the relation of congruence modulo n satisfies the properties of an equivalence relation. These are, first, the reflexive property. For all a and z, a is congruent to a mod n. The symmetric property. For all a, b, and z, if a is congruent to b mod n, then b is congruent to a mod n. And third, the transitive property. For all a, b, c, and z, if a is congruent to b mod n and b is congruent to c mod n, then a is congruent to c mod n. Now, the congruence class of a modulo n, which is denoted using square brackets, is a set of all integers that are congruent to a modulo n. The congruence classes partition z into disjoint subsets. In this section, we want to define a group theoretical analog of congruence. We'll start with an example that relates back to congruence modulo n. So let's let G be Z, the group of integers under addition, and let K be the subgroup of G consisting of all multiples of 3. Equivalently, this is the cyclic subgroup generated by 3. So this will be K is equal to the cyclic subgroup generated by 3, which is the multiples of 3. So it's a set of all 3n as n ranges over all integers. And let's let A and B be elements of Z. We want to show that A is congruent to B mod 3 if and only if A minus B belongs to that subgroup. So according to the definition now, A is congruent to B mod 3 holds if and only if 3 divides A minus B, which holds if and only if A minus B is equal to 3n for some integer n, which holds if and only if A minus B is an element of K. So this shows that A is congruent to B mod 3 if and only if A minus B is in the subgroup K. And so this proves the result. Now in the example, we showed two integers a and b are congruent modulo 3 if and only if a minus b, which is the same as a plus minus b, belongs to the subgroup K. From this example, we can abstract a definition of congruence for elements in groups, which is contained in the following definition. So let's let K be a subgroup of a group G, and let's let A and B be elements of G. Then we say that A is congruent to B modulo K, that's the subgroup, which is denoted with the notation shown, provided that A times B inverse is an element of K. Now, as mentioned earlier, congruence modulo an integer is an equivalence relation. The next theorem shows that congruence modulo a subgroup is also an equivalence relation. So this is Theorem 8.1. And let's let K be a subgroup of a group G. Then the relation of congruence modulo K satisfies the following properties. So first, the reflexive property. For all A and G, A is congruent to A mod K. 2, the symmetric property. For all A, B, and G, if A is congruent to B mod K, then B is congruent to A mod K. And third, the transitive property. For all A, B, C, and G, if A is congruent to B mod K and B is congruent to C mod K, then A is congruent to C mod K. Therefore, congruence modulo K, satisfying these three properties, is an equivalence relation. Okay, for the proof, we'll start with the reflexive property. So let's suppose A is an arbitrary element in G, and we need to show that A is congruent to A mod K. And to show this, according to the definition, we need to show that A times A inverse is an element of K, and this holds since A times A inverse is equal to the identity, which is an element of K since K is a subgroup. So therefore, the reflexive property holds. Next, we have the symmetric property. So let's suppose that A and B are arbitrary elements of G. We'll suppose the hypothesis A is congruent to B mod K, and we need to show that B is congruent to A mod K. And to show this, we need to show that B times A inverse is an element of K. Now the hypothesis implies that A times B inverse is an element of K. And since K is a subgroup, then it contains inverses of its elements. So AB inverse inverse is an element of K. And since AB inverse inverse is B inverse inverse times A inverse, which is B times A inverse, then B times A inverse is an element of K, so B is congruent to A mod K. And therefore the symmetric property holds. Next we have the transitive property. So suppose A, B, and C are arbitrary elements of G. Suppose the hypothesis A is congruent to B mod K and B is congruent to C mod K. We need to show A is congruent to C mod K. And to show this, we need to show that A times C inverse is an element of K. Now the hypothesis implies that A, B inverse is an element of K, and B times C inverse is an element of K. Since K is a subgroup, then it's closed, so that tells us that A, B inverse times B, C inverse, which is A times B inverse B times C inverse, which is just A, C inverse, is an element of K. And then A is congruent to C mod K, and therefore the transitive property holds. So this proves that congruence modulo K is an equivalence relation. Now let's again suppose G is a group and K is a subgroup of G. Now since congruence modulo K is an equivalence relation, we can consider the equivalence classes of elements in G. So let's let A be an element of G. Then the equivalence class of A, which we'll call the congruence class of A modulo K, this is the set of all elements of G that are congruent to A modulo K. So this is the set of B and G such that B is congruent to A mod K. And according to the definition, this will be the set of B and G such that B times A inverse is an element of K. Or another way of writing this is the set of B and G such that B times A inverse is equal to little k for some little k in K. Now multiplying this equation B A inverse equal K on the right by A, we obtain B is equal to Ka. So we can rewrite this one more time. The congruence class of A modulo K will equal the set of B and G such that B is equal to Ka for some k in the subgroup K. And this can be written more simply as the set of Ka as K ranges over the elements of K. And we denote this congruence class by Ka, where K is the subgroup and A is the element. And the set Ka is called the right coset for A of K in G. So Ka is a set of little ka as little k ranges over the elements of K. Or, more formally, this is the set of B and G such that there exists a little k in K such that B is equal to Ka. And the left coset for A of K is the set AK, and this will be the set of elements A little k as K ranges over the elements of K. And this is the set of B and G such that there exists a little k in K such that B is equal to AK. So we have both a right coset and a left coset. Now the right coset is the congruence class for our congruence relation. The left coset, well, that's not the same as the congruence class, that's just another set that we're defining. Now the element A is called the coset representative of either Ka or AK, depending on which one we're talking about. Now when the group operation is addition, then the right coset, instead of being written as Ka, is written as K plus A. So K plus A will be the set of elements little k plus A as K ranges over the elements of the subgroup K. Now when the group operation is addition, it's assumed that the group is abelian. So the right coset K plus A will equal the left coset A plus K. So we don't need to distinguish between the two. For an example, let's let G be the symmetric group on three elements. So this is S3, and we have it written in using cycle notation there. So this consists of the identity element, which is just the one cycle containing 1. And then we have 2 3 cycles, 1 2 3, 1 3 2. And then we have 3 2 cycles, 1 2, 1 3, and 2 3. And let's let K be the set consisting of the identity and the 2 cycle 1 2. Now this will be a subgroup of S3. And we'll let little a be the element 1, 3, the 2-cycle 1, 3. And we want to compute the right coset Ka and the left coset Ak. So Ka, or K13, this is the set of all elements in K multiplied times 1, 3. So we'll start with the identity element. We'll multiply it times 1, 3, and this will just be 1, 3. And then we'll take the other element in K, which is 1, 2, and we'll multiply it times the 2-cycle 1, 3. And when you multiply 1, 2 times 1, 3, or more properly compose them, you'll get the 3-cycle 1, 3, 2. So this will be the set containing 1, 3 and 1, 3, 2. So that's the right coset for the element 1, 3 for this subgroup K. Now the left coset, we're going to do basically the same thing, but we're going to multiply 1, 3 on the left for each of the elements in the subgroup K. So this will be 1, 3 times the identity, which is obviously just 1, 3 again. And then it will be 1, 3 times 1, 2. And this works out to be the 3-cycle 1, 2, 3. So we obtain the set containing 1, 3 and 1, 2, 3. Now one thing to notice is that these two are not equal to each other. So our right coset is not equal to our left coset. And in general, for a non-abelian group, the left coset of an element does not equal the right coset of the same element. It does turn out, however, that for certain special subgroups, which are called normal subgroups, the left and right cosets are always equal. So if you end up taking the next course following this course, Math 407, you'll investigate normal subgroups. Now we earlier proved the following theorems hold in general for equivalence relations. These were two theorems in the appendix of the textbook. So this is theorem D1. Let tilde be an equivalence relation on a set A. For all A, B, and A is related to B, or A tilde B, if and only if the equivalence class of A is equal to the equivalence class of B. So the square bracket notation is used to denote the equivalence classes for those elements. And then this had a corollary attached to it. Again, let tilde be an equivalence relation on a set A. Then any two equivalence classes are either identical or disjoint. So this tells us that the equivalence classes for an equivalence relation partition the set A into pairwise disjoint sets. Now, since congruence modulo a subgroup is an equivalence relation, then this theorem and corollary hold for this relation as well. And so the following theorem and corollary are restatements of theorem D1 and corollary D2 in terms of congruence classes modulo a subgroup. So theorem 8.2 says let K be a subgroup of a group G. Then for all elements A and C in G, A is congruent to C mod K if and only if Ka is equal to Kc. So in place of A tilde C, we have A is congruent to C mod K, since that's our equivalence relation. And then our equivalence classes are the right cosets. So we're using the notation for the right cosets, Ka and Kc. So this says exactly what theorem D1 says, just in terms of our congruence modulo K relation. And then the corollary is restated as corollary 8.3, and again let K be a subgroup of a group G. Then any two right cosets of K are either disjoint or identical. Well, again, the right cosets are the equivalence classes or the congruence classes. So the corollary in the appendix says that two equivalence classes are either disjoint or identical. So in terms of the language we're using here, we're going to refer to those equivalence classes as right cosets. Now, even though theorem 8.2 and corollary 8.3 follow directly from theorem D2 and corollary D3, we'll go ahead and provide independent proofs of them here. So let's restate theorem 8.2. Let K be a subgroup of a group G. For all elements A and C in G, A is congruent to C mod K if and only if Ka is equal to Kc. So to prove this, we'll start by supposing A and C are arbitrary elements of G. Then we have to prove this biconditional statement. And to prove the biconditional, we'll prove the forward and backward direction separately, our usual procedure. So for the forward direction, suppose A is congruent to C mod K, we need to show Ka is equal to Kc. Now, Ka and Kc are both sets. So to show two sets are equal, we can show that each set is a subset of the other. So we need to show that Ka is a subset of Kc, and Kc is a subset of Ka. So to prove the first inclusion, Ka is a subset of Kc, we need to show for all G and G is an element of Ka implies G is an element of Kc. This is just using the definition of a subset. So we'll suppose G and G is arbitrary. Suppose G is an element of Ka. We need to show that G is an element of Kc. Now to show this, according to the definition of Kc, we need to show there exists an element little k in K such that G is equal to Kc. So we need to prove an existential statement. And so to prove this, I'm going to go ahead and set up my two columns. So we'll do a two-column proof. So we need to find a K, and then we need to verify that our K satisfies our two conditions, the domain, K has to be an element of the subgroup K, and the propositional function, which is that G is equal to Kc. Okay, now since G is an element of Ka, that's our hypothesis, then there exists an element K0 in K such that G is equal to K0A. Now since A is congruent to C mod K, that's our other hypothesis, then AC inverse is an element of K, which implies that AC inverse is equal to K sub 1 for some K1 in K. So now we've got a K sub naught and we've got a K sub 1, and so we'll start by rewriting our second equation there. Okay, so we've got AC inverse is K1. If we multiply both sides by C, we'll get A is equal to K1C. And then G, which is K naught A, is equal to K naught times K1C, substituting for the A. And using our associative law, this will be K naught K1 times C. And so this looks like our propositional function, so we should choose our K to be K naught K1. And then our verification is straightforward. Since K is a subgroup and K naught and K1 belong to K, then K, which is the product K naught of K1 belongs to K. And by the work on the left, we have G is equal to K naught K1 times C, which is Kc. So the propositional function holds. So this proves our existential statement. So this shows that G is an element of Kc, so proves our first inclusion, that Ka is a subset of Kc. Now to prove the opposite inclusion, Kc is a subset of Ka, first note that since the congruence relation is symmetric, then our hypothesis, A congruent to C mod K, implies that C is congruent to A mod K. So then the proof that Ka is a subset of Kc implies Kc is a subset of Ka. And therefore the two cosets are equal to one another. And this proves our forward direction. Now for the backward direction, we'll suppose Ka is equal to Kc, and we need to show that A is congruent to C mod K. And to show this, we need to show that AC inverse is an element of K. Now since K is a subgroup, then it contains the identity element E. So then A equals EA implies that A is an element of Ka. So the elements of Ka, they look like an element in K times A. So that's what A looks like. It looks like the identity element, which is an element in K, times A. So that tells us that A belongs to Ka. And now since Ka is equal to Kc, A an element of Ka implies A is an element of Kc. And this implies that A is equal to little kc for some little k in K. Multiplying both sides of this equality by C inverse on the right, we obtain K is equal to AC inverse. And since little k is an element of K, this implies AC inverse is an element of K as required. And this proves the backward direction. So completes the proof of the theorem. Next, we'll prove the corollary. So the corollary says, let K be a subgroup of a group G, then two right cosets of K are either disjoint or identical. So let's suppose that Ka and Kc are two arbitrary right cosets of K. We need to show that Ka and Kc are either disjoint or identical. So suppose they're not disjoint. We then need to show they're identical. So we need to prove an OR statement, and one of the standard approaches to prove an OR statement is to suppose one part of the OR statement is false and then show that the other part must be true. So that is, we want to show that Ka is equal to Kc. Now, since Ka and Kc are not disjoint, then there exists an element in the intersection. So there exists an element G in the intersection of Ka and Kc. Now, since G is an element of Ka, then G is equal to K sub 1a for some K sub 1 in K. And since G is an element of Kc, then G is equal to K sub 2c for some K2 in K. So then K1a is equal to K2c. And multiplying both sides of this equation by K1 inverse on the left and by C inverse on the right, we obtain this equation. So K1 inverse times K1a times C inverse is equal to K1 inverse K2c times C inverse. And on the left, the K1 inverse and K1 cancel, and we're left with AC inverse. On the right, the C and the C inverse cancel, and we're left with K1 inverse K2. Now, since K1 and K2 both belong to K, this implies that AC inverse belongs to K, so A is congruent to C mod K. The theorem then implies, since A is congruent to C mod K, that the two cosets Ka and Kc are equal. And that's what we were trying to show. So this proves the corollary. Now here are some basic properties of cosets. So first, suppose K is a subgroup of a group G, then the right coset for the identity element E, which is Ke, is just equal to the subgroup K. Second, for any element A in G, A belongs to its own coset, so A belongs to Ka. And third, for any element B in the subgroup K, the coset Kb is just equal to the subgroup K. So to prove each of these, they're all very short proofs. So for one, by the definition, Ke is a set of all elements Ke as K ranges over the elements in K. Well, but Ke is just equal to K, so this will be the subgroup K. For two, let's suppose A is an arbitrary element of G, and by the definition, Ka is a set of little ka as K ranges over the elements in K. And since E belongs to K and Ea is equal to A, then A has the form of an element in Ka, so therefore A belongs to Ka. And then for 3, since by corollary 8.3 any two right cosets are either disjoint or identical, then any two cosets that share an element must be equal. If they share an element, they're obviously not disjoint, so they must be identical. So let's suppose that B is an arbitrary element of K. Now, since B belongs to Kb, that's by part 2 of the remark number 2, and B belongs to K, which is Ke, then Kb and Ke both contain B, so they must be equal. Now, since the right cosets are equivalence classes, they partition the group into pairwise disjoint subsets. For an example, let's let G be GL2R, be the group of 2x2 invertible real matrices, and we'll let K be SL2R. This is the set of 2x2 matrices with determinant 1. So GL stands for general linear group, and SL stands for special linear group. Then K is a subgroup of G. That's straightforward to prove. And so let's suppose that M is a matrix in G. So M is just an invertible 2x2 matrix with real entries. Then the coset Km, this will be the set of all elements Am as A ranges over the elements in K. Okay, so this notation is a little bit confusing because we've got capital letters for everything. Okay, So K is a subgroup, M is a matrix, so it's an element. So Km is our right coset of M for the subgroup K in our group G. So this is, by definition, the set of all elements AM as A ranges over the elements in K. Now for any A in K, by the definition of K, the determinant is equal to 1. So the determinant of A is equal to 1. So the determinant of the product matrix AM, one of the properties of determinants is the determinant of the product is the product of the determinants. So this will be the determinant of A times the determinant of M. But we already said that the determinant of A is 1, so this is equal to the determinant of M. So what this says is the determinant of each matrix in our right coset is equal to the determinant of our original matrix M. So that tells us that the right coset Km consists of all matrices in G which have the same determinant as the matrix M. So what this says is that the right cosets for this subgroup K partition G according to the determinant. So for each non-zero real number R, there is a right coset consisting of all matrices in G with determinant R. So again, now the right cosets for a subgroup in a group partition the elements of a group. And so in this particular example, our right cosets are partitioning the elements in the group according to the determinant. So it's sort of grouping all the matrices together that have a common determinant. Next, we want to talk about Lagrange's theorem. Okay, and so we want to use our information about cosets to characterize the possible orders of subgroups of a group. And our tool for doing this is what is generally considered the single most important theorem in finite group theory, Lagrange's theorem. So we first need a preliminary result. So this is theorem 8.4, and let K be a subgroup of a group G. Then first, G is the union of the right cosets of K, so we can write that using the notation shown. This is G is equal to the union over all elements A and G of Ka. So the idea with this notation is for each element A and G, we get a right coset Ka. And then we take the union of all those right cosets. Number two, for each A and G, there is a bijection F from the subgroup K to the right coset Ka. Consequently, if K is finite, any two right cosets of K contain the same number of elements. So we'll prove these. So first, for 1, we want to show that G is the union of the right cosets of K. And to prove this, we need to show that the union is a subset of G, and G is a subset of the union. We have two sets that we're trying to prove equal, so the standard approach for proving two sets are equal is to show that each is a subset of the other. Well, since each right coset Ka contains only elements of G, so everything is happening in the group G, so then the first inclusion holds. So each coset is a subset of G, so the union of all the cosets will be a subset of G. To prove the second inclusion, we'll suppose B is an arbitrary element of G. We then need to show that B belongs to that union of the right cosets. And by the above remark, we know that B is an element of its coset Kb. And this coset is a subset of our union. And this follows since Kb is one of the right cosets in the union. So B is an element of G, so Kb is one of the subsets that we're taking the union of. So therefore, G is a subset of this union. And since both inclusions hold, then we know that G is equal to the union of the right cosets. And this proves part 1 of the theorem. To prove 2, we need to first show for each A and G there is a bijection F from K to Ka. So let's suppose that A is an arbitrary element of G, and we'll define our function f from K to Ka by f of x is equal to xa for each element x in K. and we want to show that F is a bijection. Now, since by definition Ka is a set of elements k, little ka, as k ranges over the elements in K, then every element in Ka is an image of some element of K, so F is surjective. To show that F is injective, we need to show for all x, y in K, f of x equals f of y implies x equals y. So let's suppose that x and y are arbitrary elements of K. We'll suppose our hypothesis f of x equals f of y. Then xa is equal to ya from the definition of our function f, which implies by cancellation that x is equal to y. And therefore f is injective, and so is a bijection. So this proves the first part of part 2 of the theorem. So now the second part says, consequently, if K is finite, any two right cosets of K contain the same number of elements. Well, let's now suppose that K is finite. Now, since F from K to Ka is a bijection, that tells us that K and Ka have the same cardinality. They have to contain the same number of elements if you have a bijection between them. And since A was arbitrary, this shows that every coset Ka has the same cardinality as a subgroup K. And so this proves part 2 of the theorem. Okay, next we have a definition. So let's let H be a subgroup of a group G. The number of distinct right cosets of H and G is called the index of H and G and is denoted with the notation shown. So we have G colon H enclosed in square brackets. Now it follows from Corollary 8.3 that the right cosets of a subgroup partition the group into disjoint subsets. So Theorem 8.42 tells us that in the case of a finite subgroup, the subsets in the partition all have the same size. Now if G is a finite group, then there can be only a finite number of distinct right cosets of H. So the index will be finite. So the index of H and G will be finite. However, the index can still be finite even when G is an infinite group. And we'll start with a couple examples. So let's let G be the set of integers under addition, or the group of integers under addition, and we'll let H be the cyclic subgroup generated by 3. So this will be the set of all multiples of 3. So the set 3n as n ranges over all integers. And we want to find the right cosets of H. Well, since H is abelian, there's no distinction made between right or left cosets, so we can just refer to them as cosets. So the distinct cosets of H are, well, first we have H plus 0, and this is the set of all elements little h plus 0 as little h ranges over the elements of H, which is the set of elements 3n as n ranges over the elements in Z. So the elements of H are the multiples of 3, so they have the form 3n for some n in Z. H plus 1, this will be the set of little h plus 1 as little h ranges over the elements of H. So this will be 3n, the set 3n plus 1 as n ranges over all integers. And then H plus 2, this will be the set little h plus 2 as little h ranges over the elements of H. So this will be the set of 3n plus 2 as n ranges over all integers. Now these are also the congruence classes modulo 3. We could denote them using the bracket notation 0, 1, and 2. Now any other coset will be equal to one of these three. By Corollary 8.3, any two right cosets are either disjoint or identical. So for instance, since h plus 1 and h plus 4 both contain the element 4, then they must be identical. So h plus 1 will equal h plus 4. So there are then exactly 3 distinct cosets. So the index of H in Z, which is square bracket Z colon H, will be 3. For another example, let's let G be S3, the symmetric group on 3 elements. And we'll let K be the subgroup consisting of the identity and the 2-cycle 1, 2. This is the same subgroup we had in an earlier example. So we want to find the right cosets of this subgroup K. So the right cosets are, we'll start with K1, where 1 is the identity element. So this will be, you take each element in K and multiply it times 1. So we have the identity times 1, and then the element, the 2-cycle 1, 2 times 1, which is just the identity and the 2-cycle 1, 2. And so we get back K. Well, this is not a surprise. We already said that for the identity element, the right coset will be the subgroup itself. And then if we take K times 1, 2, 3, this will be the set. You take 1 times 1, 2, 3 and 1, 2 times 1, 2, 3. And 1 times 1, 2, 3 will just be 1, 2, 3. And when you multiply 1, 2 times 1, 2, 3 or compose, you'll get the 2-cycle 2, 3. And then we'll have K times 1, 3, 2. This will be this set, which works out to be the 3-cycle 1, 3, 2 and the 2-cycle 1, 3. Next we have K1, 2. So this will be 1 times 1, 2, and then 1, 2 times 1, 2. This will be 1, 2, and 1, which is again the subgroup K. K1, 3, this will be the set containing 1, 1, 3, 1, 2, 1, 3, which is 1, 3, and 1, 3, 2. And finally, K2, 3, this will be the set containing 1, 2, 3. There's a typo there. That first element should be the identity times 2, 3, and then 1, 2 times 2, 3. And the typo carried over, it should again be 2, 3, 1, 2, 3. And so there are 3 distinct right cosets. K1 is equal to K1, 2, K1, 2, 3 is equal to K2, 3, and K1, 3, 2 is K1, 3. So the index of K in S3 is 3. For another example, let's go back to our example with the group G being GL2R, the group of 2 by 2 invertible real matrices, and K is the subgroup SL2R, the subgroup of 2 by 2 matrices with determinant 1. Now, as shown in the earlier example, for each non-zero real number R, there is a right coset consisting of all matrices in G with determinant R. So it follows that there are infinitely many right cosets of K in G. So our index G colon K is infinite. We're now ready to prove Lagrange's theorem. So this is theorem 8.5, and what it says is for all finite groups G, if K is a subgroup of G, then the order of K divides the order of G. In particular, the order of G is equal to the order of K times the index of K in G. So to prove this, let's suppose G is an arbitrary finite group with the order of G, and suppose K is an arbitrary group of G with order K and index GK equal to n. Then the index is the number of distinct right cosets. So this says that K has n distinct cosets, which we can label KC1, KC2, down to KCn. Now by theorem 8.41, the group G is the union of all the cosets. So G will be the union KC1, union KC2, all the way down to KCn. Now since these cosets are distinct, then by corollary 8.3, they are pairwise disjoint, which implies that the cardinality of G will be equal to the sum of the cardinalities of these distinct right cosets. So the cardinality of G is equal to the cardinality of KC1 plus the cardinality of KC2 down to the cardinality of KCn. Now by theorem 8.42, these cosets are all the same size, and they have the same size as the subgroup K. So KCI cardinality is equal to the cardinality of K for each I equal 1 through n. So therefore, G is equal to the cardinality of K added to itself n times, which is equal to the cardinality of K times n, which is equal to the cardinality of k, and n was the index of k and g. So this proves the formula in the theorem: the cardinality of g is equal to the cardinality of k times the index of k and g. And this equality implies that the cardinality of k divides the cardinality of g, which is the other part of the theorem. Now, Lagrange's theorem imposes restrictions on the possible orders of subgroups of a group. So, for instance, the possible orders for a subgroup of a group of order 12 are 1, 2, 3, 4, 6, or 12. That's because the theorem tells us that the order of a subgroup must divide the order of the group. So these are the possible divisors of our group order 12. So note, however, these are only possible orders. The theorem does not imply that for each divisor of the order of the group, there is a subgroup of that order. For instance, the alternating group A4 has order 12, but it turns out it does not have a subgroup of order 6. Now, we can apply Lagrange's theorem to obtain restrictions on the possible orders of elements in a group. And this is a corollary to the theorem, Corollary 8.6. Let G be a finite group. Then first, for all A and G, the order of A divides the order of G. And second, if the order of G is equal to K, then A to the K is equal to the identity E for every A and G. So for the proof, we'll start with 1. Suppose A is an arbitrary element of G. We need to show the order of A divides the order of G. So let's suppose that A has order n. Then the cyclic subgroup generated by A has order n. And by Lagrange's theorem, n divides G. So that proves 1. Now for 2, let's suppose that the order of G is equal to K, and suppose A is an arbitrary element of G with order n. Then by part 1, the order of A, which is n, must divide the order of the group G, which is K. So n divides K, which means there exists an integer t such that K is equal to nt. Then A to the K will be A to the nt, which is A to the n raised to the t, which is equal to the identity raised to the t. Since the order of A is n, then A to the n will be the identity, and then the identity raised to any power will just be the identity. So we obtain our conclusion, A to the k is equal to E, and this proves part 2. For a quick example illustrating the corollary, the orders of the elements in U9, which is the set of units in Z9, so which is 1, 2, 4, 5, 7, and 8, they are the 1 has order 1, and 2 and 5 both have order 6, 4 and 7 have order 3, and 8 has order 2. And so we see that each of these orders divides the order of the group, which is 6, as the corollary says must happen. Okay, so this finishes off part 1 of section 8.1.